Okay, much more cheerful start now that I'm recording. So this is going to be the last time I'm going to be talking about eliminations and substitutions in isolation. We are going to be coming back to the last couple of lectures of the class where we're going to try and put some of these things together and try and look at some of these puzzles. But there's a few things I just want to touch on before we move into radicals. So we covered a lot of stuff last class. If you missed last class, watch last class. It's an important class. This one I want to touch on two more things. And that's, let's talk about SN2 reactions at, I'm going to call them resonant adjacent centers. So if we think about this mechanism, and you're thinking, okay, what is the mechanism? And let's put a solvent in. I'm going to use DMSO. And we'll give it a temperature. There. Technically, it will be frozen. I'm going to make it 5 degrees. Okay. So you're looking at this, and remember that this ringy thingy means that it's just 2 double bonds. And you're looking at going, okay, this is one of those E1, E2, SN1, SN2 things. The eliminations are out because there are no alpha protons. There are no protons on carbons adjacent to this carbon. Like the only carbon adjacent to it is this carbon, and it's got like 3 bonds to carbon, 4 bonds to carbon, so it doesn't have any hydrogens to eliminate. So no eliminations. That leaves us with the SN2 and the SN1. I have a strong nucleophile, so I'm tending towards SN2. So I draw my SN2 reaction. Yay, SN2. And I'm happy. Okay. Now, I have this reaction. It's exactly the same reaction, except I've gotten rid of the benzene ring and replaced it with a cyclohexane. Still a strong nucleophile. The elimination is possible, but if we remember right, cyanide is a real stick, and it's one of those things that's in our list of things that are nucleophiles and are not really bases. And so it's still going to do its thing. Okay, so then the question is, which of these reactions is faster? Mechanistically, they're identical. Temperature's the same, solvent's the same, no differences there. We have a primary iodide in both cases, no differences there. The only difference is in one case we're attached to a benzene ring, in one case we're attached to a cyclohexane ring. How does that affect anything? Well, if we think about the transition state, iodide's leaving, cyclohexyl, 2 hydrogens, cyanide's coming in. So I'm looking at that thing, and here we've got a very similar transition state. Benzene ring. Cyclohexyl, cyclohexane. Yeah. I guess I could have drawn the 6-membered ring. That probably would have actually been faster. Like cyclohexyl is the substituent that is cyclohexane when it's a substituent. So we have this. Again, this looks pretty freaking similar, and it does. So this doesn't really help us, and I'm just randomly drawing lines. Can I stop doing that, please? Does this work? There we go. This doesn't really help us differentiate. There's no overall negative charge, and these are transition states. So I'm indicating that's a transition state by putting in a cross of Lorraine. I'm indicating there's an overall negative charge on this thing by putting in a negative charge outside the bracket. It's split between the cyanide and the iodide, of course, at this point. Okay, this doesn't really help me very much. These look pretty similar. So what else can I think about? So when we're thinking about a speed of the reaction, we need to think about the stability of the starting materials and the energy of the starting materials. And what we're thinking about there is how easy a bond is to break. So our starting materials for this reaction, yeah, wiggly bonds. I'm not sure what the wiggly bonds have to do with anything, but yeah. The starting material for this, yeah, bonds can move. Wiggly is good. That then normally wiggly is more stable because if things can move, things are happier. The cyanide's the same, the solvent's the same, the temperature's the same, all that's different, and we have primary iodides in both cases, but they're not the same primary iodide. Because let's think about what's going on with the benzene one. Because we know that a carbon-iodine bond is polarized, right? Delta minus, delta plus. Back to lecture number 2 or something. Okay. That's the same for both of them. I am not helping anything here. Now, am I telling the whole truth here? Are these the same level of polarization? And why? Okay, well, the iodine's going to pull the same amount in both cases because it's iodine. But these carbons are different. This carbon, if it's starting to become delta plus, you know, it can pull a little bit of electron density from the carbon adjacent to it. And it's a primary carbon. It's got a hyperconjugation influence with the carbon next to it. Cool. It also can pull through induction. So both interactions through space. There's no empty p orbital, so the I shouldn't have said hyperconjugation. There's no empty p orbital here, so it's just pulling down through the bond. There's no empty orbital that can interact, but it can pull electrons. Oh, it can pull electrons through that bond. There are no eliminations in this reaction because cyanide is the nucleophile and cyanide is a crappy base. And so it just doesn't do a base thing. It's a stick. It just does the nucleophile thing. But if you're starting to generate more of a positive charge here, you got more flexibility because the carbons next to it can do resonance. Now, they can't resonate into this guy. That's sp3. There's no resonance into that. But I can draw a good resonance structure. Well, I can draw a resonance structure where the benzene ring can put a negative, that should be a negative charge, next to that delta positive. Is it a great resonance structure? No, I just created charges where there weren't any charges before. But it's possible. So I'm going to think that if this guy is becoming slightly positive, the benzene ring is able to move a bit more negative charge onto this carbon to compensate, which allows this iodine bond to become slightly more negative, or iodine to become slightly more negative. So we're able to kind of compensate because we can make this positive bigger so this iodine can pull harder because we have resonance next to that center. So we can stabilize a growing positive charge here. And if we're doing that, we're making this iodine more negative. And what does that mean we're doing if we're making the iodine more negative and a carbon more positive? It means we're weakening that carbon-iodine bond. Because the iodine is pulling more of those electrons towards it, the carbon's getting less of the electrons. And if the iodine is pulling more of the electrons towards it, that bond is becoming less covalent-like. The iodine is becoming more, it's almost becoming more of an ion pair, where you have I minus and C plus. Now, you definitely don't have that. You have a covalent bond, but it is not an even covalent bond. So this is a weaker bond than that one. So in this case, because this leaving group is on a carbon, that is adjacent to an aromatic system or a system that can do resonance, we have weakened that bond between it and its leaving group. And if we've weakened that bond, weaker bonds are easier to break. So this guy is more reactive. And it's not a little more reactive, it's like 10,000 times more reactive. And it's all because as you start, that iodine can pull more of those electrons. It can actually kind of pseudo break that bond ahead of time. And you can think about it being, hey, that's a pretty stable carbocation I'm making there because it's benzylic. It's got all that resonance with that. So it's not that bad if that's a carbocation. The iodine can bring more of its electrons its way. It can be more electronegative. All these different ways of thinking about it, they all come down to the same argument. You're weakening that carbon-iodine bond. And you're weakening it before the nucleophile even comes on the picture. So once the nucleophile arrives and it sees these two options, this is by far the faster reaction because this bond is already weakened. It's already kind of breaking. Yeah, 10,000 times is about the difference between a reaction difference between these two. So A is about faster than B. And 10,000 is a big number. So I just want to highlight that point. Yeah, exactly. Because of a weak bond. Basically what we've done is we made iodine a better leaving group. It's kind of like we made it into super iodine. It's like if we had, it's like the different, it's kind of on par with the difference between bromine and iodine or chlorine and iodine. More like chlorine and iodine. So it's like we've made it into a much better leaving group because, not because we've changed this atom, but because we've made the starting material more unstable. Or we've given the starting material a weaker bond. Okay. The next thing I want to talk about, and because we briefly bounced over it, I don't want to manage my notifications. I don't know, make this go away. My lock, oh, okay. Okay, there we go. Yeah, no, yeah, I know. It's whenever I try and move my cursor over to the right hand side of the screen, it tops up the notification box. What I want to talk about is PDC oxidations. And I want to talk about these because we briefly touched on this when we talked about the oxidation and reductions. And I'm just really unhappy with how I discussed that. So we've got two of these agents, and you can use either. So we got PDC and PCC. PDC is pyridinium dichromate. Doesn't matter. These do exactly the same thing. I kind of use them interchangeably. Mechanistically, apparently I'm drawing PDC down here. You can just draw one if you need to do one, because you can pick whichever one you want. And I'm only ever going to ask you about PCC because they're very similar, but PCC is mechanistically a little simpler because it doesn't have as much stupid stuff going on. Oops. Actually, we are going to be talking about PVC. That's that might actually be later this lecture. That's a Cr chromium in the middle here. And the reason I'm coming, and so the reminder what these things are is they are mild oxidants that oxidize alcohols to aldehydes. They do not go all the way to acids like the Jones oxidation. The reason I'm coming back to these guys is chromium loves oxygen. All the metals love oxygen. Oxides are what exist in nature, right? You find lead oxide, chromium oxide, rust is iron oxide, and that's what iron wants to become. It's just we live in an oxygen-rich environment, and oxygen is really, really reactive. Like it catches fire and stuff, or I guess it fuels fires. Everything wants to burn. So let's think about an alcohol, primary alcohol. So we did this mechanism, and what we're going to do is we're going to add PCC, and we're going to bring it up to the aldehyde, and it is going to stop there, and we're going to discuss why. And I want to talk about this because this is an E2 elimination. Yeah, alcohol to aldehyde. That is exactly what I said. These are both alcohol to aldehyde. They'll also go to ketones as well. But that all depends on what your alcohol is. If it's a secondary alcohol, it'll go to a ketone. Okay, so that's what we're going to discuss. So mechanistically, if you can recall, I'm sorry I just said that. I really hate it when people say, if you can recall. This is going to react with, I'm going to do PCC. That's what I've said. And I'm going to protonate the chromium, and it's going to grab, and the way this is going to work is it's going to temporarily grab a hydrogen from the pyridine that is next to it. Normally you do this in aprotic solvent. And we'll talk about why it's aprotic. Dichloromethane is great. So we'll have this. You know, if we think about this for a second, we have a chromium-chlorine bond, and we know chlorine is a good leaving group. So it shouldn't surprise us too much if what happens is we get an SN2 reaction on chromium displacing chlorine. That's all it is an SN2. So we're doing an SN2 kind of as a sub-step of this mechanism. And I'm missing an oxygen. And so we have that. Okay. Now, we are essentially, and there's HCl, because so we've just released, I've just you know what, I'm going to be anal. We have a proton there, and then we can bring in Cl minus, and it can steal this proton. And I'm going to ask you to forgive me. I'll let you do this too, so I guess we're even. Another equivalent of HCl that was generated by another one of these, we're going to donate a proton to this guy. So we're doing plus minus H plus. We're moving protons around. And you could write plus minus H plus. Yep, that is an SN2, and the chlorine is a leaving group. And now we're doing an acid-base reaction right here. Yep, that is a proton transfer. I just wanted to draw it out because I just realized I was skipping a step. I'm going to pretend I didn't see that, Andrew. My blood pressure is high enough. Actually, I don't know if my blood pressure is high or not. I'm at that point where you're lack of sleep, where you're not quite sure if you're tired or not, or hyper or high. So we've got pyridine present. Yes, all of the above. And essentially, we are doing, I want you to think about what this is. This is just an E2. We are taking, if we think of it this way, that this is the alpha proton. This is kind of like the carbon with the leaving group attached. And the leaving group in this case is this whole chromium thing. And it's kind of dealing with it by losing water. But it could be either one. Both those H's are the same. What we get is we get an aldehyde and we get chromium dioxide. So, and we generate one equivalent of water. Now, if you remember in the Jones reaction, we did that reaction in water. And the next step was water came in, attacked the aldehyde, made the hydrate. But there's just not enough water present here because you're not making very much water. So you don't make the hydrate. And if you can't make the hydrate, you can't oxidize this any further. So we don't go to the acid under these conditions because you don't have all that water in there that you have when you do with the Jones reaction, which is the chromic acid in sulfuric acid or chromium trioxide in sulfuric acid. So what I wanted to highlight here is that we just have an E2 and an SN2. So these reactions we've been looking at, a lot of them are just substitutions and eliminations and substitutions. There's only so many things going on underneath the sun. And so I just wanted to make sure I revisited this. Okay. What I'm going to do now is I'm going to make people cry. So we're going to switch to introducing radicals. That is the wrong year. So this slide is on Blackboard. If that's how you want to follow along. But you can. We're not going to get into too much detail. So what I'm doing with this lecture, hopefully, is we're going to talk. We're done with eliminations and substitutions. That's it. We're going to talk a bit about some radical chemistry, and we're going to just revisit thermodynamics and kinetics. We've already done it, but we're going to just briefly talk about it again because it comes in again here, and you can never talk enough about thermodynamics and kinetics. Well, you probably can. I like it a lot. So this is chapter 19 in your textbook, and I'm going to double check and make sure it's chapter 19 in the textbook. So I've got the textbook right here. Yeah, it is. Good. So we're going to just discuss some of the concepts and terminology that we use in radical chemistry. We're going to talk about the stability of radicals, and the next two things we're going to get to on Monday, which is the free radical halogenation of alkanes. We're going to talk about radical polymerization. And we're going to talk about the anti-Markovnikov addition of these halogen things, which I've said, trust me, we're going to come back to that. Well, it's time. We're coming back to it. Is there supposed to be stuff on this slide? Oh, okay. So this is often the first reaction that is shown in an organic chemistry course, and there's a reason I didn't do it, because the reason they do it is because it's an alkane, and alkanes are simple, and so the chemistry of alkanes must be simple. So let's start with the chemistry of alkanes. And the chemistry of alkanes is not simple. So what you do is you take methane, you take chlorine, you heat it or you shine light on it, and you get chloromethane and hydrogen chloride. Knowing the chemistry we know to date, this is black magic. Like, there's no nucleophile here. Like, methane, it's all CH bonds. It's got nothing. How does this happen? And it happens using radical chemistry. And radical chemistry requires tons of energy and weak bonds. That's the secret. And it often needs heat or light to initiate it. Well, it needs energy, and energy normally comes in the form of either heat or light. For this one, the most effective wavelength is blue because that's absorbed by chlorine gas, so the chlorine can absorb the blue light. What it does basically is you start vibrating that chlorine bond back and forwards really, really fast. So this starts really vibrating. It's already kind of weak, and it kind of vibrates itself apart. So with blue light, and it vibrates itself apart and the bond breaks. Now there's different ways. I want to make sure I know what's coming next when I click the button, and then it's probably not what I want. We're going to come back to this idea of chain reaction, but one blue light event is going to make multiple products, not just one product. You're going to get multiple copies of chloromethane and hydrogen chloride. So what I want to talk about is what's going on here. So we take blue light and we start shaking that chlorine-chlorine bond. It absorbs it. This is actually why my lab, we have a blue lamp that shines things in blue, and it's for breaking chlorine-chlorine bonds. So you start shaking it, the bond starts vibrating, and now let's think about the ways that bond can break. So if you have a chlorine-chlorine bond, you can break it by moving both of the electrons onto one chlorine. You get Cl plus and Cl minus. And this is kind of what we've done so far in this course. It's just we've used double bonds as a nucleophile to attack one of the chlorines. So we never actually get Cl plus. Because this Cl plus is 6 electrons. And just like oxygen with 6 electrons, that sucks. That's like a positive chlorine, and that just doesn't exist. So this is not a good way to break a chlorine-chlorine bond. The other way we can break the chlorine-chlorine bond, so this is called hydrolysis. Lysis meaning breaking, hetero meaning different. So we have different breaking. So one of them is positive, one of them is negative. In contrast to that, we have homolysis. Lysis meaning breaking, homo meaning same, and so we break the same. Yeah. Okay. So what you'll note is I am drawing single hooked arrows. So far, all of our arrows have been double hooked. And that's because 2 electrons are moving when we draw that arrow. It's also because that's what arrows are. When people draw arrows, they draw double hook because that's what arrows are. But when we figured out what radicals were, and we realized it was a single electron moving, some genius decided, the way we'll indicate this is we'll have a single hook. Because 2 hook means 2 electrons, 1 hook means 1 electrons. And what we end up with is 2 chlorine atoms. Right. Yeah, I don't know if it was Fisher who figured that out. Probably. It's my guess. Now, if you look at this, you go, oh, that is not something I want to be doing. Because let's think about what's happening here on a molecular level. And this is really simple. It's 2 molecules. So each of these chlorines is sp3. Well, actually, they're not hybridized if they're not making bonds. But let's say the chlorine decides to be sp3. And there's another chlorine which is also sp3. This is chlorine. This is chlorine. There's an extra electron in here, my mistake. These two can make a more stable molecule by combining 2 of their sp3, singly occupied sp3 orbitals to make a bond, a sigma bond, right? Sigma, sigma star, put 2 electrons in there, make chlorine, chlorine. Well, this is why things make bonds, because they can put electrons in lower orbitals. It's the entire reason why things make bonds. We're going to come back to heterolysis and why we do homolysis. Heterolysis is what happens all the time. No, in demercuration, so Mariam asks, is this what happens in demercuration step with sodium borohydride? No, that is actually H minus attacking the carbon, displacing the mercury. That is actually still ionic. That is still 2 electrons moving in every case. I've really tried to avoid talking about radicals to date. I think they've slipped out a couple of times, but I'm really tried to avoid talking about that. So we're going to come to when you do radicals. Everything is heterolysis except radicals. And for radicals, you need energy, and you often need a sensitizer. And we're going to talk about both of those things. Did you get pressure to teach us this? No, this is important. This is. I don't really get pressure to teach you anything. We had a long discussion about whether we should do carbonyl chemistry in this class, and I was on the losing end of that discussion. I thought it should wait till the next course, but we had a discussion that for some people who are not going to take the next organic but are going to take biomolecules, they should see some carbonyl chemistry first, and so that makes sense. So that's why we did that. I think this is important. I find this confusing, and radicals have upset me. So I'm kind of upset because radicals upset me. They're not beautiful. So I disapprove of their lack of beauty. But why things make bonds, we went back to like class number 1, why you get H2. Why do 2 hydrogen atoms come together and make a bond? Is because when they share that electron, they can put it into a sigma bond, and that's lower in energy. And so when 2 chlorine atoms come together, they want to make a bond. They don't want to be chlorine radical, chlorine radical. They don't want to be chlorine atoms. They want to make chlorine bonds. But put enough energy into the system, and you can break that apart. Now, it's temporary. Hopefully these 2 drift apart, because if they don't drift apart, what's going to happen almost immediately is, oh, we're going to remake the bond because that's more stable. Put a little asterisk next to the unstable, because there are some radicals that are really, really stable, but we're not going to talk about those in this course. In general, radicals are unstable. They are like carbocations. They form, they react, they're no longer there. They're transient intermediates. They are intermediates. They're not transition states. They do exist. You can actually see them, and you can measure them, and you can watch them do things. But they're not stable molecules. And that's because they really want to make bonds. They don't want unpaired electrons. we have not drawn a lot of unpaired electrons, and that's because those things are unstable. They want to be in a bond. So what we're going to be talking about in the radical portion of this course, and the good news is I think this lecture timing is going to work out nicely, is what's called the free radical chain reaction. And I don't know how many of you guys are familiar with this. There are three main steps. There's initiation, generates a radical intermediate. Propagation, the intermediate reacts with a stable molecule to produce another reactive intermediate. And termination, side reactions that destroy the reactive intermediate. So I'm going to sort of talk about this in, using an example. And I think the next thing I'm going to talk about is kinetics before I get into this. But there's three main steps. I'm going to add a fourth step. I call it pre-activation. Generate a radical that is not an intermediate. This step sometimes is the same as initiation and sometimes is different. And when we see mechanisms, we're going to see you can call this pre-activation, you can call this activation. I'm fine either way. Sometimes this is the same thing as initiation, sometimes it's different. So the overall reaction for this is, okay, well, that's not what I actually want to talk about. Okay, well, let's talk about, okay, so initiation is clearly not on the slide. In this case, there is no pre-activation. We're going to talk about why when we get to an example with pre-activation. But I give this blue light. HV is a symbol for light. Because it's Planck's constant times wavelength. And what we're doing is we're going to generate two chlorine radicals as we just showed. That's initiation. I have made radicals that are intermediates in this step. And I'm trying to click and it's not clicking. So in propagation, I'm making my products. And so you can think of initiation as there were no radicals and now there are two radicals. That's normally a sense of activation, but I don't want to get too complex in this. Okay, Bavian sent somebody a note that I think he meant to send to me, but he accidentally sent it to everyone, except he sent it to someone else first. Cool. I'll let you sort out whatever happened there. So the chlorine radical reacts with something, and what it's looking around for is the weakest bond to react with. Chlorine does not want to be a radical. It wants to be anything but a radical. It's going to react with something. So what actually happens generally, and it's not productive, is we've got two things in solution. We've got methane, which for no particular reason we're drawing with no stereochemistry and in a disgusting Fischer projection. And we've got chlorine. And we have a tiny amount of radical at any one time. Like tiny. I mean tiny. Like you might have a 1 liter flask with like tons of stuff in it, and you might have like 20 radicals in there. There's very little at any one time. They're really unstable. They don't exist for long. But if you have a chlorine radical floating around, it's looking at both of those and it thinks, what do I want to react with? I want to react with the weakest possible bond. I want to break the weakest possible bond. The weakest possible bond is a chlorine-chlorine bond. So 99.99% of the time, this is what happens. So what are those arrows meaning? This means, I'll draw in all the lone pairs in this guy, that this chlorine radical is meeting a single electron that came from this chlorine-chlorine single bond in the middle of space. And so what that means is with these two kind of coming together, I'm making a new bond between this chlorine atom and that chlorine atom. So this nomenclature, this convention, is that the two arrows kind of come together, because it's not this electron going to the other chlorine, it's kind of joining up with one of the other electrons to make a new bond. And what happens there? Oh, look, I get chlorine-chlorine plus a chlorine radical. That is the reaction that's happening most of the time. We would call this a non-productive reaction, because our starting materials and our product are the same thing. So it literally did not create a product. It was non-productive. That's where that word comes from. It's just other people have stolen it from chemists, which is okay. The productive reaction is the very rare time that the chlorine accidentally takes a hydrogen. That's not, the carbon-hydrogen bonds are pretty strong. There's no particular reason why it's going to do that. But occasionally it does it by accident. And what happens there is you generate a methyl radical and hydrogen chloride. Then if I click, something should happen. Oh, I'm on the wrong screen. Now the second propagation step is, oh God, you've got a carbon radical. And that is not happy. We're going to talk about why that's unhappy. So it's looking for the weakest bond to break. That's still chlorine-chlorine. Hasn't changed. So this makes sense. Carbon radical interacts with the chlorine-chlorine, and we generate a chlorine radical. And we have chloromethane. Note that this is where we started. So now we go back and we do this again. And again. And again. And again. And so this is a chain reaction, because once you start getting this chlorine into this, it can just keep doing this cycle over and over again with fresh methane every time. So overall, what ends up happening is this. Now, the products of the reaction, this is really, really important. When we draw these mechanisms, and we're going to go through a bunch of these examples in the next couple of classes, we're going to draw activation, initiation, propagation, termination. So the last thing you draw is termination. But termination does not give you the products of the reaction. The products of the reaction come from propagation. Let me write that again. That's really important. It's worth writing. Products of radical reactions come from propagation. So if I asked you what the products of this reaction were, you're not done the mechanism. You're not at the end. We're used to being, when you're done the mechanism, that's when you got the product. The products of this reaction are chloromethane and hydrogen chloride, because you're going to make a million of those for every termination step. So although termination is the last thing you draw, it's a million to one. No, you can heat things. So Mohammed asked, is light the only way you can increase the amount of radicals in a reaction? No, you can heat things. You actually never want a lot of radicals in a reaction. They react really, really fast. And so they're far faster as reactions than anything else, because they are so unstable compared to everything we've seen. It's kind of like if you had lots and lots of carbocations floating around at one time. You don't. You have a small amount of carbocations, and as soon as the carbocation is formed, it reacts. And you make a little bit more, and then it reacts. It's the same thing with radicals. Radicals are constantly reacting. That's why free radicals are bad, and you need to use... there is no termination on this slide. Termination is when two radicals come together. Hopefully there's space. Yeah, perfect. My next slide is termination. Termination is when two radicals come together to give you zero radicals. So initiation, zero radicals became two radicals. Propagation, one radical became one radical. Termination, 2 radicals become 0 radicals. We're terminating a reaction. We are killing the radical. Now, we got 2 different radicals in this system. We have a chlorine radical and we have a methane radical. And you kind of have two choose 2. There's 3 ways to do this. So you can have a chlorine radical interact with the methane radical to give us chloromethane. We can have a chlorine radical interact with the chlorine radical to give us chlorine. Or we can have a methane radical interact with the methane radical to give us ethane. Or we can get rid of the radical because everything on the last step was the overall reaction there on the quin. So the last step on this slide is just the overall reaction. This is because the products of the radical reactions come from propagation. So the products of methane plus chlorine in the presence of heat or light is chloromethane and hydrogen chloride. But mechanistically, we're not done yet because we still got a radical floating around, so we got to get rid of that thing because it's unstable. The other way this can happen is your radical can collide with the wall. And the wall is the wall of the flask. It's often metal or it's glass. And you can interact with the silicon or you can interact with the metal and you can basically stick to your surface. And you make kind of a coating along there because your radical is collapsing to the surface of your whatever thingy is. And this is actually a problem. Eventually you foul a lot of glass if you do a lot of radical chemistry in it. The entire inside of the glass becomes coated with hydrocarbons or something because that are covalently bound because you've made radicals and they've bounced into the wall. So termination in all these cases is we are getting rid of radicals. Next class, we're going to start with this slide. Okay, this is a good question, Kimia. Which one has more effect on the rate of the reaction, ratio of the solvent or the temperature? Depends how small the differences are. So if a temperature difference between a reaction is 1 degree, like let's say one is run at 59 degrees and 60 degrees, then who cares? Probably your solvent ratio matters. If one is run at 20 degrees and 0 degrees, 20 degrees is a lot hotter. That's a lot faster. So you got 2 things that really affect rates of substitution eliminations that you can really play with besides playing with the structure of things. And that's how hot you heat it and how much you make the environment conducive to the reaction occurring. Temperature is normally really important. If the temperature gap is really, really small, the solvent matters more. But if the temperature gap is big, temperature is always going to matter more. That should be it's kind of intuitive, hopefully.